What's up, everybody? So we're approaching the end of Physics 207, and at the time I'm recording this video, it is April 12th of 2024. I mean 2025, and our third exam is on the. Let me pull up a calendar here. Our third exam for 207 is on the 22nd of April. I think. Let me make sure. And so I thought it would be beneficial to start studying for this now, because this exam immediately precedes the final, the comprehensive exam on the 25th of April. And so I thought we could just get started earlier, because I know I record these videos mostly for myself. Sorry, but and then I upload them 2 days before the exam starts, so it's not as helpful. But maybe if we start earlier, we can get some better studying in. Usually I do the exams before I take the video, or just kind of do a glance over and then do it. But today I thought we would just do a complete dry run of 2017's exam, because I've been told by some friends that this exam is the hardest one out of all the practice exams. And so I thought we could take a crack at this, starting early. So this is gonna be a dry run. I mean, we're gonna work through this. I'm gonna be explaining a lot more of my thinking. This might be an hour-long video, honestly, but hopefully this helps somebody, even just one person, to be helpful. But yeah. So I already did the first question before I recorded the video, but we're going to go through it again because it was a little weird. But the other three questions I haven't seen yet, except for technically the third one, but I'll explain that later. But the second and fourth question I have never seen before. So, and I know the fourth question's about RC circuits or something like that. Usually it is, and so that'll be differential equations, but as we've been taught. But we'll see where this gets us. I'll have to probably pull up some old notes or something later to get us through that question, and maybe we won't even get that through question. But let's just get started here. Okay, so the first question we have is about this. Okay, so consider a long, infinitely long hollow cylindrical wire. The wire has outer radius f, and the cylindrical hole at its center has a radius d. So, looks like it got cut out here. This iPad's dying, dude. It's crazy. But, that's yellow, isn't it? Okay, so this outer radius of this thing is f. The inner radius is d. And then we have a current I1 flows through the left and the right, from left to right, and the current is uniformly spread over the region. Okay, that's important to know. And then at the center of the wire is an infinitely long cylindrical wire of radius A. And it has a uniformly spread current I2 going from right to left. Okay. Let's go ahead and highlight this. Okay, so find the magnetic field everywhere. Let me just put that. Okay, so right away, whenever it says infinitely long wire, and it's cylinder, and it tells us the shape, I would automatically think of Ampere's law, because that's kind of a derivative of Gauss's law in the world of magnets and stuff. So I'm no physicist, but I would say that's probably our best bet here to tackle this question. So we'll most likely, and I have the exam answers and stuff on my computer here, so I'm going to be taking a look at those. And I also have the laws listed, or the useful information page as well, this one. So I would say the first law we would use here is Ampere's law, which is this one. B dot dr equals mu naught I enclosed. And yeah, that should really be all we need at this moment. Another concept we'll probably use is for uniformly spread currents, which states, and this is only for uniform currents, uniformly spread currents. I enclosed divided by I total equals A enclosed divided by A total. So that's pretty useful. We didn't really get that so much with Gauss's law, the charges, but we can use it here. I might be wrong about that, but I'm pretty. It's been a while, but it's been pretty confident that this is the concept. This isn't necessarily a law per se, but it is something we will most likely use. So let's get at it. So when I first did this question, I stupidly did the outer wire first, which was kind of a mistake. So let's do the easiest thing first, which is just doing this inner wire here. So there's going to be two magnetic fields, to be considered from this inner wire. So let's first get an equation for the magnetic field using Ampere's law. Since it's uniformly spread, we can say that the magnetic field's most likely constant, so we can just take that out. Constant enough to be taken out of the integral. Which we can then say we can equate this. We can compute this integral to just be the slices we're taking of this object, which are circles, because it's infinitely long. Or sorry, not circles, but circumferences from this thing. We're growing larger and larger, encompassing more of it. But yeah, so if you want to know more about why we're doing this, okay, so what it's going to come out to be is the magnetic field, whatever it is, times 2 pi r, which equals mu naught I enclosed, which we can then say equals mu naught I enclosed divided by 2 pi r. In some direction, we don't know that yet. And the reason it's 2 pi r is it's from Gauss's law. So we're taking these circular, slices of the cylinder and expanding outwards from the axis that goes through the center of the object. And so we're encapsulating more of the magnetic field or the current as a, as a function of the radius that we're choosing, So that's what we're doing. And if you want to know more about that, I did the videos that I did for exam 2 extensively cover Gauss's law, which is very comparable to what we're doing. So what about the direction? Because magnetic field's a vector quantity. It is a direction. So using the right-hand rule, I know you can't see me, but if you point your right hand, your right thumb in the direction of I1, or let's do I2 first. If you're just pointing towards it, we have the magnetic field's going into the page here and coming out of the page here, right? So that's what's going on. And so we can then kind of derive a coordinate system. We probably should have done that first. I'm sorry. But I guess, okay, let's say that positive x is in this direction. Because if we're looking at current 2 first, we might as well put the positive x in the same direction as that. And we'll put y going up. And then I guess we can have z going into the page. Okay, so that's our coordinate system. Perfect. We're not going to know the direction yet, but we'll get there. Again, this is a dry run, so I'm sorry if this is kind of silly and largely inaccurate. But it's good to kind of just take a swing at what we know. This is a practice. Okay, so let's get started here. So we'll find the okay. So now we need to find what I enclosed is at different points or different radii along this cylinder. So we'll start at the smallest amount of radius that we can have, which is r less than a. Okay, and so because we're inside the object that's carrying current, we need to take portions of I2 to find what I enclosed is. And so using this equation that I talked about earlier, we can say that I enclosed is going to be equal to I2 times the enclosed area, which is a function of r, divided by the total area, which is a constant value, because we were given that its radius is a. Okay, so let's see. So we have I2 times r squared over a squared. Okay, then we can say that the magnetic field 1, the first magnetic field, is, we can just plug this value in for I enclosed from here, this equation. So we have B1 is mu naught times I naught, or sorry, I2 times r squared over a squared over 2 pi r, which we can then say is, we can then put this up, the r's will cancel, and so we'll end up having mu naught I squared r over 2 pi a squared. Yeah, and that's what I ended up getting for when I first went about this question. Okay, so the magnetic field would be going, if you're looking from the side, I guess it would be going counterclockwise. Yeah, okay, that's fine. Now let's do this space between A and D. Okay, so D less than R less than A. Okay, so what we just did is we took like little circles growing from the center of the area of the wire, and we're growing along it. Okay, and we're encapsulating more of the charge. More of the current, and until we get to A. And so that's why we took portions of it, because we weren't grabbing all of it in all those cylinders, all those circles, those circular slices, So when our radius grows beyond A, these signs would be flipped. When the radius grows beyond A, we're taking slices that have a radius larger than A. And since the object that carries current 2 has a radius of A, if we're taking Gaussian slices with a radius greater than A, we're effectively capturing all of that current. Again, if that's confusing, I did a lot of Gauss's law in the videos for exam 2, so you can watch those again. Really similar stuff. It's just current now. And so when the radius is greater than A and less than D, we have that I enclosed, and that's I enclosed by the Gaussian surfaces, by the Gaussian objects, is I2. And so we can just say that B2 is mu naught I2 divided by 2 pi r. And that will be also counterclockwise. Okay, so that's the inner wire. Now I do the outer wire. And by outer wire, I mean this one with current 1 running through it. Okay, so we're going to be doing a radius between... We're going to do the radiuses, or the radii between D and F. So we'll have R less than D, R greater than D and less than F. So since we're, again, taking slices growing outwards from D, we're grabbing more and more of current 1. as we expand. So we will again do I enclosed equal to some portion of the total current. And that portion coming from the ratio of the variable area and the total area. Okay, so one thing I got wrong when I did this question, and I kind of thought about before I recorded this video, is that we're here, right? We're at radius d, and we're taking these slices of these slices that are meant to be capturing charge. In addition to capturing portions of current 1, we're capturing all of current 2, because this slice is not just taking this portion of current of the wire, that's current 1. We're also grabbing all of current 2 as well. So we need to subtract that, or really add it, because current I1 is going in the negative x direction and current 2 is going in the positive x direction. So what we have is we have current 2 minus current 1 times its fractions, or times the ratio of its radius, of its changing radius over the total. And so, we're doing what we did here, but for current 1. So current 1, its variable radius is going to be pi times r squared minus d squared, right? Because if we just did r squared, then we wouldn't be doing, we wouldn't be where we want to be. We want to subtract d from r squared. And then we're going to divide that by the total area, which is f squared, the outer radius of the entire object, and the inner radius of the wire. And then we can just say that equals I2 minus I1 times r squared minus d squared over f squared minus d squared. Okay? Okay, cool. So let's continue on here. So, all right, cool. So now we can plug this into our equation for the magnetic field. So we'll have magnetic field 3 equal to mu naught over 2 pi r times I2 minus I1 times r squared minus d squared over f squared minus d squared. Let me save this real quick. And then this is something I'm a little confused about, and I'll have to come back to later, but the key says that this is also counterclockwise. I'm not entirely sure why that is, other than, maybe I2 is stronger than I1, and in this case, since we're subtracting portions of I1, I2 is technically greater. I don't know. I'm sorry, but it is in counterclockwise direction. I know that the direction is pretty vague for me there, but if we're really thinking about it, current 1, if we use the right-hand rule, its magnetic field is going to be coming out of the page here, and then it's going to be going into the page, here. So I'm not necessarily sure about this one, and I'm going to have to ask questions, but the exam's a ways away, kind of, and so we have some time. I know that's not super comforting to hear, but it is counterclockwise, and we'll circle back to that. Maybe I'll think about it more. But okay, sorry about that. But okay, so now we'll do when the radius is greater than f, and now again we've completely enclosed both I1 and I2 at this point, and so we can just say I2 minus I1 is our I enclosed, which we can then say B4 equals mu naught I2 minus I1 over 2 pi r, which is also in the counterclockwise direction. And I think it's that concept of everywhere that we really need to think about. I don't know. But the physics itself, the math, that we would need to do, the Gaussian surface, that's all been tackled at least, so that's good. But I will endeavor to figure out why this is also counterclockwise. Perhaps it's a mistake. I don't know. It probably isn't, but it is, because in my mind it would be clockwise, but I don't know. When I was first doing this video or doing this question, I was, instead of putting counterclockwise, I was just putting, into the page, because that's also an acceptable way of writing this down. I also don't know in what context the question is, what coordinate system the grader or the person who did the solutions for this exam chose, because they could have been looking at it from, facing the flat end of this cylinder, and I'm taking it on from another perspective. So I don't know, but we'll move on from this for now, and we'll go to this question. Okay, so mind you, I have not done this question yet at all. So we'll figure it out. Okay, so a very thin circle of wire lies in the XY plane. It radius r. Okay, that's what's weird. It has radius r. Positively charged particle d, or q, sorry, is a distance d away from the center of the circle, moving with a velocity v, as shown. Okay, so this is the q. This is the charge q, I guess. Okay, the force on the particle when it is at the point shown is measured and has the known magnitude F and points into the page in the negative x direction. What is the current in the circle of wire? Okay, so we're looking for the current in this wire, I guess. Okay, so that's cool. Let's take a stab at this. I would say what we probably want to use here, because we don't know what the magnetic field is. We need that. I would say we're going to use the Biot-savart law, maybe, because we're given it's a distance d away from the center of the circle, moving with velocity v. Okay, so things that we know. The laws we're probably going to use. Since we're given force, we'll probably need to use QV cross B. And in cross products, let me try and remember this. I think it's like the magnitude of AB sine of theta, the sign between them, and it's sine of pi over 2, which is equivalent to sine of 90 degrees, is equal to 1. Okay, that's gonna. I need to write that down. Sorry, that came in my head randomly. I think that's what that is. Just in the event that we need to use that. Okay, so we have the force from the magnetic force on this charge, and then we're probably also going to use Biot-savart law, which we can write as dB. The derivative of the magnetic field is mu naught I over 4 pi times ds cross r over r cubed, which we can, say is magnetic field is equal to the derivative. Okay, r cubed. Okay, so we're looking for I, right? We're looking for the I that is in this loop over here. And so what I would say me to do, also this might be the last question I do, because I didn't realize it's already 8:40 and I need to go do something at 9. So I might make this a 2-part video. Anyway, so let's see. We have the Biot-savart law. Okay, that's good. So I would say our first step here is this Q, this charge. This diagram is horribly drawn. So this is D. I would imagine they meant to put like a curly bracket there, or whatever the hell you would say, to show the distance. So this charge q is a distance d from the center of the object. Okay, so let me get out this. The last time I used Biot-savart was on another question that is inconveniently on my iPad. Okay, well, that's not good. It's fine. We'll figure it out. So let's see here. Again, we're learning. This is fine. Let me just pull up some old notes from my laptop here on when we use Biot-savart, because it's kind of weird. Like, it's not that hard, but it's still like, ooh, I don't know, but we'll see. Okay, so I think this was chapter 11 when we used this. Okay, I lied. It wasn't. It was chapter 10. So chapter 10 has the Biot-savart laws if you're in this class anyway, but just need this to remind myself what we're doing. Okay, so yeah. Okay. This is good. This is perfect. Awesome. Okay, so let me see. Okay, so to use Biot-savart, we have this radius, or this r vector there, right? And so r is going to end up being d squared well, I think it's going to be d squared plus y squared. Sorry, all this is out of order. Apologize, but the magnitude of r squared, or the magnitude of r, this thing here, and the reason I think it's this is because this particle is moving up, at a velocity v, and that means this like component of the vector is changing with y, whereas this component along the z-axis, I think, is not changing at all. It's just constant. It's d squared. As we were told, it's a distance d from the center of the object. And so I think we're measuring the magnetic field from the center, which is, that's perfectly acceptable, I think. So that's what I think is going to happen. I could be totally wrong, but we're gonna figure it out. So the magnitude of r is equal to the magnitude of, or the square root of d squared plus y squared. Okay, so these are the components of the vector. Y squared is a variable; it's changing. Right. Okay. So and then d squared is constant. Okay. So which means r is going to be equal to d z hat plus y hat. I guess I could just do y's I hat z, I hat y. Right, so that's what we're going to say the r vector is for Biot-savart here. That's usually what I like finding first when it comes to this. And then ds is going to be, in the same direction as the current, so we're going to be taking slices of the object here, which is going to have some arc lengths, I guess. Okay, so ds, we can say, it has a radius arc, so we were given that. Okay, it's perfect. So we can say that ds is most likely going to end up being, it's a small s, by the way. That's kind of important. So ds is going to be these infinitesimal slices of the loop, which we can, describe as arc lengths. So we can say that ds is going to be r d phi. Okay, and where the hell did I get from? Okay, so if we're looking at these sorry, this is really bad. Okay, so let's say we had the circle here that has a current flowing on it, and then we're taking these ds slices, and this is the center of it. Then we're going to be taking these little, slices of it, and that's going to have some, okay, let's say like we're taking little portions of it of angle phi, right? And imagine this is like infinitely small, then that's what we're going to be doing. Okay, so hopefully that helps. I don't know. Kind of rushing now. I'm sorry. But fair enough. So we have ds equals r d phi. Okay, so now let's move the Biot-savart law down here. Mu I over 4 pi times the integral. Okay, so let's figure out what ds cross r is. R is going to be. Using this kind of idea, I would say that they're perpendicular to each other. In the z, okay, so the z component of r is orthogonal to ds, which means we can just say that ds cross r in the z direction is r ds, I think, based on this law, this rule here, since 90 degrees would imply that they're perpendicular. Okay. That's good. And we know that ds, we're saying that ds equals r d phi. And we want the limits of integration, or we want to take the integral here with respect to something that is an angle, like theta or phi, because we are going to be ultimately, because Biot-savart is, just, it's about, sorry, I'm my head's like scrambled right now, because Biot-savart uses the current in this loop, and the loop is a circle. We're going to be taking the integral over the circle, over the the radius, over the angle of the circle, the entire angle, all the phi's added together, we don't need to get into calculus here, but like the limits of integration is going to be from 0 to 2 pi, right? So that's what we're doing. Okay, so I like this. So we can say that we have r times r d phi. Sure, let's do that. Let's run with that. And then we said that r is equal to this, so we have r cubed. We plug this into r cubed, so we have d squared plus y squared. Ooh, I don't know about this, guys. This is a really, really ugly integral. We might need to take a step back and think about this again. Oh my god. Okay, so yeah. Okay, so wow. Okay. Let me think about this. I'm trying to look at my notes at the same time. Well, technically we're taking this integral with respect to phi. So y, although is a variable, it isn't necessarily. It's a constant in regards to this integral itself. So I guess we could run with this for now, and we'll just kind of see where it gets us. Because I really don't think there's really another way we could do this, per se. Maybe there is. I don't know. Trying to think because we cross R, DS, and R because DS is along the loop, and R is. Okay. Well, let's think about it this way. Because like if we took R to point from the loop to the, from the loops, the circumference of the loop to wherever Q is, then the Y component of it would be R plus Y. R plus Y times I hat Y plus the Z component, which would still be D. And so either way, we're getting a constant D squared there. A constant D I hat Z times I hat Z. So, and that would be what we theoretically think it is. And that's still a pretty ugly integral. So, yeah, let's go with what we have right now. We'll circle back to this if we need to. Okay, so we can go ahead and just pull all this out because it's, it's all constant relative to what the integral is respect to, and in respect to, or being taken in respect to, which is from 0 to pi, the integral of 1, Okay, so I feel like I'm just talking nonsense at this point. Okay, so that's going to end up just being, 2 pi, right? So we can cross out our pi's here. So we have the integral, or we have mu naught I over 2 times r squared over d squared plus y squared to the 3/2 power. Okay, so that's a pretty reasonable magnetic field equation, I would say, and this is going to be in the IZ direction. And how I got that is, if you use the right-hand rule again, and your thumb is pointing in the direction of the current, your right thumb is pointing in the direction of the current. The magnetic field is going to be, if from at the center of the loop, or the center of this loop, the magnetic field is going to be going in the positive Z direction. Because the right-hand rule states, like you have the curl going this way. Hopefully that's helpful. I don't know. Use the right-hand rule, guys. It's awesome. Okay, so now we have our magnetic field. Cool. Let me go ahead and label that as such. Whoa. What the hell just happened? Okay, so we have that B equals this. Okay, so we have our magnetic field. That's cool. So now what we need to do is use this force equation to solve for the current, because this is what we're solving for, the current in the loop. Okay, so let's do it. Okay, so the force on the particle when it is at the point shown is measured and has the known magnitude F. Oh, this is huge for the program. Okay, so if we're, correct me if I'm wrong, the force on the particle when it is at the point shown, so when it's at this point, that's what we're measuring it at. So that means we could plug in R for Y, right? Because if we're saying this is R, the R vector, and these are the components of it, and we're only worried about the force at this point right here, then if we only know the force at that point, then we can just say that Y equals R squared, or Y equals R, because that would be this component of it. Or, sorry, I said that this is it. Okay, well, I mean, this is still fine, honestly. Okay, so we'll just say this is R, guys. This is R. Okay, that makes more sense. Okay, so now we can say that this is R and this is D. Okay, so let's just plug in R for Y. And see where that gets us. So we have R squared over D squared plus R squared. This is huge. That's awesome. Okay, in if I'm thinking of this correctly, which I could also not be. But this isn't an arbitrary distance anymore. This is, we're saying that the force on the particle at this point that it is pictured to be at is known. Which implies that we're only worrying about it when it's at this point. When we know what the x, or what the z and the y component of the vector is. So we can just say that y equals r. I think. Okay, so let's go with that. Okay, so we have our magnetic field now. And now we're solving for I, because we don't know what that is. So let's use our force equation. We know the magnitude of the force is F. So the magnitude of F, the F vector at this point is F. And we know that it's into the page. So that's in the negative x direction. Sorry, that's not a negative sign. A negative x direction. So the magnitude is F and it points into the page. Okay, so the force points into the page. So it's negative F. Negative F times Ix, or in the Ix direction. Okay. I hat X. Epic. And we know that its magnitude is F. Okay, sorry. That's what we know. Known. Maybe I'm overcomplicating this question, but that's what we know. That's what it's told us. Okay. So now we need to use the force equation, which is, I had that somewhere. Where was it? Oh, yeah. Okay. So this is QV hat cross B hat. We know what V is, and we know what B is, and we know what Q is, and we know what F is. So we can just plug all this in, right? Okay, so if it's into the page, if the force is into the page, and B is in the Z direction, and QV is moving in the Y direction. Okay, so the magnetic field's in the positive Z direction. Q is moving in the Y direction. Then that means their cross product is, that means they're they're perpendicular to each other, right? Yeah. Which means that the angle between them is 90 degrees. So that we can use this concept for the, the cross product. This value for the cross product. Which is the magnitude of, or the absolute value of A times, A times B sine theta. Where sine theta is 90 degrees. Or sine of 90 degrees, which is 1. Okay, so let's run with that. Okay, so let's plug all these values in. So we know, using that concept that I just said, we can technically, and this is going to be really bad math, but good physics, possibly. So F equals, and the force is end of the page, I should probably say. I'll probably write that down too. Okay, so F is end of the page. Yeah, okay, cool. So that means we have Q times V times the magnetic field R squared over D squared plus R squared d squared plus r squared to the 3/2 direction, to the 3/2 direction, the 3/2 power. And then that's we're going to do the absolute value of that. Right. Okay, so, because we've said, it's sine of pi over 2, because that's the orthogonal angle. They're perpendicular to each other, so these two things are perpendicular to each other, in theory, based on what we said. So sine would equal 1. Sine theta would equal 1. All right, so then we can just, let's have mu naught qv r squared times I, which we're solving for, qv mu naught r squared, qv mu naught r squared. Let me put q and v by themselves and mu naught in the center. And then we have 2 times d squared plus r squared to the 3/2 power equal to f, I think. Okay. Yeah, now I'm gonna be late to my thing, but that's okay. I'm enjoying this. I'm really learning right now. I hope you guys are too. Maybe you're not. This is a lot of nonsense. But anyways, we'll just multiply this over to f. So 2f times d squared plus r squared. I feel like I'm making things up at this point. Divided by that stuff in the numerator, mu naught r squared. And that equals I in the wire. Okay, moment of truth. Let's look at the answers. Let's see what we got. Dang, this is a really wacky question. Oh no, guys. I got it right. Let's go. Okay, so we made some correct assumptions. I feel like my TA would be really disappointed in me. But we have figured it out. We've solved this problem. This is awesome. So yeah. This is great. Okay, so yeah, the answer is I equals 2f times r squared plus d squared quantity to the 3/2 power divided by q times, or mu naught times q times v times r squared in the counterclockwise direction. Okay, so that, looking at it, yeah, that makes sense. Okay, so let me grab this. I forgot about the direction of the, whoa, okay, what's happening? Okay, so, wait, actually, let me just copy and paste it. So this is our final answer. This is so exciting, guys. What is happening? Okay. Oh, it's vanished. Okay, so we'll just say I equals that counterclockwise. So it'd be going this way along the loop. Okay, so when I first drew this, I guessed it correctly. Cool. Yeah, okay, so we did it right. That's awesome. Okay, so with this question, I guess I'll give like a better overview of it. I guess, okay, so we're given this charge and it's moving at a distance. It's a distance d away from a loop of wire that has a current in it, and this current is inducing a magnetic field at the center of the loop, or just kind of everywhere around in this plane. And we're asked, we're given the force that's exerted on this charge by the magnetic field and the direction it points in. We're given the velocity and the charge and the distance, the two distances, and we're told what the force is at this point. Right. Okay, so the reason we use Biot-savart is because we're given a charge Q. Or we're really given a point away from this loop that is experiencing the magnetic field generated by the loop. And so we're using Biot-savart because Biot-savart has the R vector cross the ds vector. So you wouldn't want to use Ampere's law for this because, and you theoretically could, but it makes more sense to use Biot-savart because we're using vectors here. So, yeah. As I said, the radius, I'm not acting like I know what's going on, but like the R vector, its components at this point where, its components, given that Q is on the z-axis at this moment in time, where we're given the magnitude of the force, its components are R and D, right? So R, IZ, and I guess it would technically be negative IZ, maybe. But yeah, so that's the components. And then DS is, so all these Y's are wrong. I would just, take out the Y wherever you put it and put an R instead. It just kind of makes more sense to have it at that. But, in theory, this could be a variable distance. Right. So, but we're only really concerned with it being on the z-axis because that's where we're given the force. That's the point in which we're given the force. Okay, so, yeah, awesome. We did it right. Good job, guys. Okay, so, yeah, awesome. I've got to go for now, but I'm going to make a part 2 of this video, and we'll get back to that whenever I have time. But I don't, this question I've done something similar to it in the past. So this one won't be too bad, but this is the one that I really wanted to work on because I haven't really spent much time on these RC circuit questions, and they're pretty weird because they involve differential equations. But there is like a systematic approach to these questions that we can look at later. But like I said, I'll make a part 2 of this video, and I'll probably, try to thoroughly explain this question because I know like a lot of this I seem to just be pulling out of my butt, like, magically. But I really did just raw dog this question. I'm surprised I got it right, honestly. But, oh, wow. How'd that happen? Yeah. Okay, so, yeah, I'll make a part 2 of this video, and we'll do the second half of this exam. But thanks for being here. Good luck in your studies. Hopefully this maybe helped. I don't know. It helped me, to be honest with you, but we'll get there. Okay. I'll see you guys in the next video.